been talking about the rates of reactions. We've talked about rate constants. Most chemical reactions are sensitive to temperature, which means that you change the temperature and the rate's going to change. Let's all be really quiet and see if they notice. Hi. I'm starting lecture now. So an example is a 10 degrees Celsius increase in temperature could double or triple the rate of a biological reaction. So that's a huge change, 10 degrees Celsius difference. So, the rate constant is a constant, right? Well, it's constant if the temperature is constant. If you change the temperature, the rate constant is going to be different. So I know that's a little disappointing because I like things that are constant, but you have to, whatever. So the temperature dependence of the rate is due to the temperature dependence of the rate constant. And that's what we're going to look at today. This is known as the Arrhenius equation. This shows the relationship between the rate constant and the temperature. So here we have the rate constant is equal to a frequency factor, A, times an exponential factor. So this is e to the x, where x is negative EA over RT. It's kind of complicated. So this is the anti-natural log. Up here we have the activation energy, which I haven't talked about yet. R is our friend, the gas constant, using these units, joules per mole Kelvin, so 8.314. And T is the temperature in Kelvin. Okay? So let's talk about the activation energy and the frequency factor. So this is an energy diagram. So we show energy increasing as we go up on the y-axis and the reaction progress on the x-axis. And you saw these in Chem 1A. They may or may not have been meaningful to you. But here we have the reactants are starting at a higher energy and the products are ending at a lower energy. Is this an exothermic or endothermic reaction? It's exothermic because heat energy is coming out, and that's why these are lower. Okay? Well, there's a little more to the story. It's not just this and that. There's what happens in the middle. So for most reactions, there is some sort of an energy barrier in the middle here. That's called the activation energy, the energy barrier that has to be overcome in order for the reaction to proceed. So this looks a little bit like a miniature golf course to me, where, it'd be the side cutaway view, right? I didn't do this for the class yesterday, but. So here's you with your little putter, right? I'm not an artist, I'm a chemist. And you're going to hit the ball, and they have all these weird humps and bumps and stuff. And you have to hit the golf ball so it goes up and over, and then it rolls down, and the hole's down there somewhere, right? Well, if you don't hit it hard enough, it's just going to roll up a little bit, and it's going to roll right back. You have to hit it harder. You hit, it almost went over, right? So you're hitting it really hard. You hit it too hard, and it goes flying. Well, it went over. It did go over. But you need to get this minimum amount of energy, that much or more, for the golf ball to go over the hump. And so that's what the activation energy is like. The reactants here, in order to react, have to have enough energy to get over the barrier. Yes?
Can you put in too much energy?
If you put in too much energy, it's fine. It still reacts. Yeah. It might, I guess you could envision it as going up here. It's still going to go down there. It'll be fine. Yeah. So the activation energy is the height of this bump that has to get over. The frequency factor, A, is the frequency. So how many times the reactants try per unit time. So that would be equivalent to how many times per second or per minute you hit the golf ball. How many times do these reactants try to get over the barrier? That's the frequency factor. So we're going to look at a simple reaction in which methyl isonitrile rearranges to form acetonitrile. So these chemical formulas are very similar. The difference is that here this nitrogen is attached to the CH3 group, and here the carbon's attached to the CH3 group. How does it go from this one to that one? Well, something has to happen here. This has to flip around. So that molecule starts out like this. It has to go through a high energy intermediate state where that nitrogen carbon triple bond thing is kind of pulled away and twisted. So if you imagine these hooked together with rubber bands, you imagine that you could take these two guys and kind of pull them and twist them, but that would require energy, right? It's not going to want to be that way. You'd have to put energy into it. So in order for it to get to this position where it's twisted 90 degrees, it needs a certain amount of energy. At this point, it could go forward or it could come back, right? This is going to move one way or the other. So you need energy to weaken the bond between this carbon and the nitrogen and let this thing rotate. EA is the activation energy, the energy needed to reach the activated complex or the transition state. So when that's twisted, that's like the transition state. That's a state it goes through in the middle. If this barrier is higher, the reaction is going to be slower. So think back to the miniature golf, right? Well, if the hump is really big, it's going to take you longer to get the ball over, right? If it's really low, everything you hit might go over, right? And if there was no barrier, as long as you hit the ball, it would go and keep going, right? Any questions? Yeah.
Is the frequency factor, is that the same as a collision rate?
The frequency factor is related to collisions. We may or may not get to the collision model today. So the frequency factor is the number of approaches to the activation barrier per unit time. So that NC group, we say, approaches the activation barrier each time it begins to rotate. Sometimes it rotates just a little and it goes back because it didn't have enough energy. Oh, it went a little further. No, now it didn't go as much. And it's like trying. And so the frequency factor is the rate at which that group wags. It's like a dog wagging its tail, right? So it goes part way, it wasn't enough, but how many times does it try per second, say? That's the frequency factor. So the more frequently it tries, the sooner it's going to be successful, right? If it only tries once an hour, it's going to take a really long time because not all of those things are going to be successful. So the frequency factor was the A in the first part, and then the exponential factor represents the fraction of molecules that have enough energy to get over the activation barrier. So we've got that carbon-nitrogen group wagging, right? The number of times per second it wags is the frequency factor. The rest of that equation set gives us the fraction of molecules that are successful. It's a fraction, so that number is going to be between 0 and 1. If none of them are successful, it's 0. If all of them are successful, it's 1. If you wanted a percentage, you take the fraction and multiply by 100. So the fraction of approaches that are successful and result in a product. So if the frequency factor was 10 to the 9th per second, which is really high, and the exponential factor was 10 to the minus 7, meaning that only 1 out of 10 to the 7th tries was successful. That's real low chances, right? It's a good thing. People don't see chances like that because we would quit. But the molecules don't care. to find the rate constant, we're going to take the frequency factor times the exponential factor. And so for this one, it would give us 100 per second. So the frequency factor, how frequently they try to react, the exponential factor, how successful they are, the fraction of successful attempts. Any questions?
Mrs. K?
Yeah.
So that's just A times E to the RT.
This here is the exponential factor. E to the negative EA over RT. This is the exponential factor.
Oh.
Yeah, so the whole Arrhenius equation is A times this. So that's the frequency, and this is the exponential factor. The exponential factor is going to depend on the activation energy, and it also depends on the temperature. So if we have a low activation energy, we've got E raised, this is always going to be a negative exponent. This negative exponent is going to be small, right? If EA is small. If T is big, that's also going to make this smaller. So with a low activation energy and a high temperature, the factor can approach 1, where everything is successful. Low barrier, more energy because of the temperature. If the activation energy is high and the temperature is low, it can approach 0, where none of the approaches are successful. And it's helpful to remember that temperature is a measure of the average kinetic energy of molecules in a substance, right? So at a high temperature, the way I think about it is, there's the 3 physical states of students. So right now, you guys are a crystal and solid, because you're sitting in rows, right, and you're not moving around. Are you absolutely still? No, thank goodness. Everyone seems to be breathing, right? Some people are taking notes, some people are fidgeting a little, that's fine. So in the liquid state is when we have lab and you're milling about. And the gas state is at the end of class, we open the door and you effuse out the door and you spread out, right? But in the solid state, if we increase the temperature, that's like you guys getting antsy. Like maybe I give you all Red Bulls or something. And you start, you're having a hard time staying in your seat. You're wiggling, right? So even in a solid, you have a higher kinetic energy. It's just that they're not going anywhere. If you have a liquid or a gas, the particles are actually moving through space faster at a higher temperature. Okay, so increasing the temperature here, is going to make this factor smaller, which is going to cause this to be closer to 1, more successful. Any questions? Yeah.
What does R stand for?
R is the ideal gas constant. Yeah.
What if they're both high?
If they're both high, they're going to kind of cancel each other out. Or if they're both low. So what we're doing here is we're just looking at the extremes. So you're going to have not much success, a lot of success, when the activation energy is low and the temperature is high. And the opposite is true when those are reversed. And in between, it's a combination. Depends on the relative sizes. Any other questions? Yeah.
So the exponent to the D would be 1, or the outcome?
This whole term would be 1.
Okay.
So, this whole thing would be 1. Yep.
Why isn't the A included? Is that just because it's just showing us that specific?
Do you mean this A?
No,
The big A. So the big A is the frequency factor, and this is the exponential factor. The equation, the rate constant equals the frequency factor times the exponential factor. So we're just looking at them separately because we just need to understand how they work. Okay? So molecules in a sample have a range of energies. Like, you look at students and somebody might be asleep on their book, right? Very low energy. Somebody else forgot to use the bathroom before they came and they're just like, right? Higher energy. So in a sample at a given temperature, there's a range of energies. So here we've got fraction of molecules with a particular energy. The blue is at a colder temperature, and so we've got kind of a Gaussian distribution here. And we see that, the average is around in here. But some are higher and some are lower. Okay? This would be the activation energy. Only the molecules that have energy equal to that or higher can actually react. So if you like calculus, it's the area under that curve, right? Those are the guys that can react. When you heat up a sample, the average temperature increases, but that's not all that happens. This doesn't just slide over, it spreads out. So we're still going to have some with very low energy, so this is like fixed. So when the average moves out, the whole thing spreads out. So the area under the blue curve and the area under the orange curve are equal to each other. They're different shapes. So when this spreads out, now a bigger portion of that has enough energy. And so the number of molecules that are able to react goes way up, right? It's not proportional to the temperature. Any questions? So this is just a summary. Frequency factor, number of times that the reactants try to react, approach the barrier. Exponential factor, fraction of approaches that are successful. That exponential exponential factor will be higher. More of them will react if you have increasing temperature and lower activation energy. So it increases with increasing temperature, but it decreases with increasing activation energy. Okay, let's test ourselves. Which statement best explains why reaction rates generally increase with increasing temperature? So we have three choices here. They each have a lot of words in them. The first part is the same in each. Reaction rates increase with increasing temperature because. The first one says, as the temperature increases, a greater fraction of molecules have enough thermal energy to surmount the activation barrier. B says, as the temperature increases, the pre-exponential factor of the rate constant increases. The pre-exponential, that would be the frequency factor. And the last one says it increases because molecules decompose into their constituent atoms, which can then form new bonds to form the products. What do you think? It's A. So, at a higher temperature, more of the molecules have enough energy to get over the hump. This is talking about the frequency factor increasing with temperature, and it really doesn't change very much with temperature at all. We haven't talked about that yet, but we definitely did not learn this. It's not true. And this just sounds nice, right? It just sounds good, that's all. Any questions? Yeah.
You said it doesn't change with the temperature, it doesn't matter if it goes up or down.
What we're gonna do is conveniently ignore it. Yeah. And that comes right here. The temperature dependence of A is relatively small and is often ignored. So your 1A instructor might have said, confess that they were lying to you. about stuff, right? It's not really lying, it's more simplifying, right? Just leaving out unpleasant exceptions. So we are going to be learning about some of those things in 1B, but there's still going to be some things where we're like, this isn't a really big deal, so we can just ignore it, right? Because if we pay attention to every single thing, it's crazy complicated, right? And so that A factor doesn't change very much. And so it really doesn't have an effect on the rate constant unless you're looking at extreme temperature changes. The other thing is anytime you're measuring any of these things, measured quantities have error in them. And so, the difference in A might be within the error of the measurement. And so you're not even going to see a result of it being different. So you can just ignore it. So frequency factor and the activation energy, how do we find those? We can measure the rate constant at different temperatures. We can take this, the Arrhenius equation, and rearrange it and make a linear form of the equation. And you don't need to understand how that happens. If you want to see how it happens, I can do it with you in lab, but I'm not going to do it for the whole class. Just rearranging so it's in a linear form. We're going to see lots of linear equations, right? Y equals mx plus b. So here on the y-axis, we have the natural log of the rate constant. The x-axis is going to be 1 over the temperature in kelvins. So we graph natural log versus 1 over the temperature. The slope is going to be negative EA over R. The intercept is going to be the natural log of A. If you're having a hard time assigning these letters to parts of a linear equation, please ask me during lab, because once you see how that works, it makes everything much easier. Okay. So when you plot data like that, it's called an Arrhenius plot. It's based on the Arrhenius equation. So we're going to look at the decomposition of ozone. It's important in many atmospheric reactions. So they studied the kinetics of the reaction, and this is the data. So they measured the rate constant at a bunch of different temperatures. Okay. This says determine the value of the frequency factor and the activation energy for the reaction. So what we need to do is we need to make a graph. And the Arrhenius plot is natural log of K versus 1 over the temperature. So you would need to do some calculations on these numbers. For temperature, you need 1 over the temperature. So that'll be 1 divided by 600. 0.00167 for each of those. You calculate. I left out the t because this is x. So we have 1 over t here. That's represented by x. X is 1 over t.
I'm sorry, for the slope, it was negative EA over RT.
Thank you. I made a mistake. Yep. The t is not supposed to be there. Let's see. There. Thank you for seeing that, because that's confusing. Yeah. Okay, that better? So can we find the activation energy? Sure we can. We have a mathematical equation. It looks like it has 2 variables, but R is the ideal gas constant. R is equal to 8.314 joules over moles times Kelvin. So this is one where it's probably easier to rearrange the equation before. So I'd multiply both sides by r. I'm just going to get rid of this part. Multiply by r over there. The r's cancel out. Now I have negative EA is equal to this other thing. So I'd multiply both sides by negative 1. So EA is equal to negative 8.314 joules per mole Kelvin times the slope, negative 1.12 times 10 to the 4th. What are the units of the slope? It's the units of y over the units of x. When you take a natural log of something, what do the units do? They go psst, right? They're just like gone. So we've got no units, call that 1. And what are the units on the x-axis? It's 1 over t, and t is in Kelvin, so it's 1 over Kelvin. So 1 over Kelvin is the same as Kelvin. So this has units of Kelvin. I'm just showing you this to show you that the units work out. We're not going to try to trick you with units, except when it comes to joules and kilojoules, and that's going to show up all over the place. So it's not really a trick then, right? Because we do it all the time. Okay, so negative 8.314. I forgot to get the calculators out. If you guys want calculators, feel free to grab them. They're in this little cupboard down there. So what are the units on that?
Joules per mole.
Joules per mole. The kelvins are going to cancel out. So that's the activation energy. Yeah.
I'm trying to find out how you got positive
I multiplied both sides by negative 1. Multiplying this negative by negative 1 gave me a positive. Because it started out as negative EA over R. And then I multiplied both sides by R, and I multiplied by negative 1. And so that canceled this
So
out.
did that make the slope positive?
Well, the slope is negative. EA is positive.
But when you distribute the negative,
Well, yeah, when you distribute this negative over here, yeah, those two negatives cancel each other out. But that's not the slope, so the slope's not positive. But that side of the equation is positive. Yeah. Any questions? Okay, activation energy. So that is the y-intercept. So this is natural log of A. I should have done this. So the y-intercept is equal to 26.8, and that equals the natural log of A. So here I solved this using some algebra. Could you use the number solver on the calculator? Absolutely. Here, you could use the number solver as well. I realize that's a really sad 6. Looks a lot like a K. So use the number solver if you like, or the algebra method is we need to get rid of natural log, so we do the inverse function, which is inverse log. So we're gonna do e to both sides. E to the 26.8 is equal to e to the natural log of a, which is equal to a. So a is going to be e to the 26.8. I'm just gonna write down 3 sig figs. That's a really big number. Sometimes really big numbers mean that we did something wrong.
I don't like big numbers.
Yeah, I'm with you on that sometimes. The little tiny ones are also kind of scary. So remember what the frequency factor is. It's the number of approaches per unit time, say per second. And so 10 to the 11th times per second is really high. But molecules are crazy small, and they can do that. So this frequency factor can be really huge. Then the exponential factor is often very small. Yeah. Any questions? So they express the activation energy in kilojoules per mole instead of joules per mole. And there's the frequency factor. So for that same example, use the results to predict the rate constant at 298 Kelvin. And I put this in here so that we don't have to try to remember and go back. So we're going to use the Arrhenius equation. So K is equal to A times E to the negative EA over RT. We've got A and EA that we calculated before, and this is T. Um, 93.1 kilojoules per mole divided by 8.314 joules per mole Kelvin times 298 Kelvin. It's a mess. This is an example of where you could get tripped up with kilojoules and joules. Activation energies are typically large enough that they're expressed in kilojoules per mole. So, on the previous screen, we saw what it was in just joules, but we're going to pretend we don't know that. So we're given this, kilojoules per mole, but the units on the gas constant are joules per mole. And that does matter. It's a common error on exam questions. And you'll do all this hard stuff right, but you forget to convert from kilojoules to joules, and the answer's wrong. So there's multiple ways that you can convert. My favorite is to just erase the kilo, move these guys over. What does the kilo prefix stand for? 1,000, or times 10 to the 3. So I'm going to write times, I'm going to write with the eraser, it doesn't work, times 10 to the 3. That's a really easy way to make that prefix go away. And you can do that with any of the prefixes. So now when we look at the units, we've got joules canceling and moles canceling and K's canceling. Now, would you have to write all the units in there? Not necessarily, but you need to pay attention to the units. You would need to notice, oh, this is kilojoules, and then my gas constant is joules. I better do something about that. So then you put this mess into your calculator. So you can just do the whole thing at once. And if you can do that, you don't need me to show you how. If that sounds daunting, what you might want to do is calculate what's in the parentheses first. So that's going to be 93, turn the calculator on, 93.1 EE3 divided by, and then here's another potential tripping point. We're dividing by this times this. And you can use the fraction button on your calculator, or you can put parentheses around these guys. If you don't put parentheses down there and you go this divided by this times 298, it's going to take this fraction and multiply the whole thing by 298, and your answer is going to be off by a factor of 298 squared. So we don't want to do that. So I'm going to divide by parentheses 8.314 times 298, close the parentheses. That negative is still there. There were more digits, but that's what I wrote down. Yeah,
You can even make it a little easier and do constants on the calculator, the ideal gas constants in there.
yeah. Yeah, you can use constants on the calculator. I've never done that on this calculator because I just remember the numbers. But yeah, there's lots of stuff hiding in here. It's good stuff. Okay, everybody get the 37.577? Okay, so now we can finish this off. 4.36 times 10 to the 11th times e to the negative 37.577. I have my calculator set to show me things in decimal notation, which most of the time is good. So I can convert that to scientific notation, or I can make my calculator do it for me. If you press the mode button, which is right there at the top, and move the cursor, the first line's deg, rad, grad, and go down to norm, sci, eng, and go over to scientific notation, sci, and hit enter, and then quit to get out of there, and then you're sad because your number's gone. Press enter. It comes back. So this is 2.0893 times 10 to the minus 5. How many sig figs do we probably want? Probably 3. So let's call this 2.09 times 10 to the minus 5. What are the units? I tricked myself with this yesterday. Now I know. We're not going to get any units out of this, are we? There they are. They gave the units over here. That's the only way you would get the units. So it turns out this is a first order reaction. I'm sorry, a second order reaction. So we can put the units in there because they told us what they were. Any questions? So I got 2.09 and they got 2.07. Should I worry about that? No. The last digit is the uncertain digit. A little bit of difference there isn't going to matter. How could that happen? Well, if you use the unrounded values, you'd get a more accurate result. Well, what if you don't have the luxury of all that data, or being able to do all those experiments? You can still get a lot of information if you have the rate constant at 2 temperatures. So measure the rate constant at 1 temperature, measure it at another temperature, and you can still calculate the activation energy. You can't calculate the frequency factor, but the frequency factor is not useful for most things. So we don't care about that. So this is what's known as the 2-point form of the Arrhenius equation. And again, if you're interested in how you would get this from the linear form, I can show you, but I'm not showing the class because most of you don't care. So this is useful when your data is limited or you don't have the capability to graph something because you don't need to make a graph. So consider the reaction between nitrogen dioxide and carbon monoxide. The rate constant at 701 Kelvin is measured as 2.57, and at 895 Kelvin, it's 567. Find the activation for the reaction in kilojoules per mole. So we have a bunch of numbers in here. Let's highlight the numbers, because usually the numbers are more important than the words. So those are the numbers we're given. So let's write those down and label them. So 701 Kelvin, that's a temperature. I'm going to call it T1 because it's the first temperature I came to. 701 K, the measured rate constant is 2.57. Those two go together, right? 2.57. So I'm going to call that K1, which is a nickname for my first child. Didn't start until the third one, though. At school, they started calling him K3, Kawagoha 3. Yeah. K6 is still at that school. So then we come to another temperature, 895 Kelvin. So that's a temperature, that's the second temperature. And we get another rate constant, 567, and that's K2. If you called both of these 2 and both of these 1, you're going to get the same answer. But if you mess up the partners, it's going to not work. They're in pairs. So we're going to plug this into the 2-point form of the Arrhenius equation. You can plug this whole thing into the solver and solve for EA. Or maybe you want to save it a little bit of work and do this side, just calculate the value of this side. You can also solve it for EA on your calculator just from that without doing anything by mentally rearranging it in your head. I don't advise doing that unless you and algebra are really, really good friends. So choose your way to solve it. Let's solve this problem. I want to know how you got it to go so fast. That was cool. So that's the answer. What are the units? Yeah, so these, the kelvins are canceling out. And this part would be going to the other side, and so it would be upside down. I mean, we're multiplying by joules per mole on both sides, and so this is the this this is the unit I want, and this is the one I want to get rid of. So that's dimensional analysis. You look at the units first, and then you stick numbers in there. Because even in Chem 1B, people do kilojoules to joules backwards sometimes. Easy to do. And so the kilo's up here, and then we ask ourselves, what does kilo stand for? 10 to the 3. So 10 to the 3 goes down there. Up here we wrote kilo. That's like a different name for 10 to the 3. So we're never going to put them next to each other because a joule does not equal 1,000 kilojoules, right? So I'm going to take my number here and divide by 1 times 10 to the 3, and I'm going to get 1.45 times 10 to the 2 kilojoules per mole. Yeah, 145. But I remember from yesterday that they wrote 1.5 times 10 to the 2. So they felt like they should have 2 sig figs. Mine would round to the same. Any questions? Okay. Use the results from example 15.8, still the same example. And the given rate constant of the reaction at either of the 2 temperatures to predict the rate constant at 525. So we're supposed to use one of these rate constants and its corresponding temperatures to find the rate constant at a different temperature. I'm just going to use the first one, 701 and 2.57. Write them down before they leave my brain. So this is a temperature, this is a rate constant. We want the rate constant at 525. So T2 is 525 Kelvin. And see what I did there? That's a 1, and there's a 2. Gotta watch those 1s and 2s. K2 is what we're trying to find. So we're going to use that same equation. And we're going to use EA that we discovered in the previous part of this problem. I'm going to use the 1.45 times 10 to the 2. Ideally, we would use an unrounded value, but going through slides like this is tough. So again, plug the numbers in and then worry about rearranging.
Wouldn't we want to use the 10 to the 5 number for the units?
That would make things simpler, wouldn't it? Yeah. So before we converted it, it was that many joules per mole. And so if you were already working with that and had seen that, absolutely, let's use that one instead. A lot of times, especially on an exam question, things aren't going to string together like this. They're just going to give you EA, and they'll give it in kilojoules per mole. So let's use the one in joules per mole. Great suggestion. So negative 1.45 times 10 to the 5th joules per mole divided by 8.314 joules per mole Kelvin. T2 is 525. T1 is 701. Bless you. So again, you can use the solver. Kind of a combination approach might be more efficient. This side has no variables in it. You just calculate that side and then put natural log of x over this equals whatever that number is into your solver and find it like that, right? So that's also the approach you would take if you were just going to use algebra. Let's find out what that side is first. I got negative 8.34052. Anybody else get that? Okay. If you're doing the solver, just quietly do your solver thing. We're trying to solve for K2, which is in this thing here inside the natural log. So we need to get rid of the natural log, and the way you do that is e to the x of both sides. So e to the x of this is just what's inside the parentheses. So e to the x gives me this. And then on the other side, I have e to the negative 8.34052. And so I would want to multiply both sides by 2.57. So there's some kind of messy math in here, right? And so, if you have dyslexia or any of those processing issues, this is going to be extra challenging for you. And unfortunately, I can't really do anything about that except sympathize. If math just muddles your brain, you're also going to have some trouble. But I would encourage you should always write down the equation with the variables in it. Write down the equation with the numbers plugged in. Where you go from there is kind of up to you. I could do this one directly from here. I could get to that. But that's not necessarily the best way for you to do it. You could plug this whole thing into your solver. Or you could do like this, calculate that side, plug this into the solver, right? And we should all end up with the same answer. Any questions? So reaction A and reaction B have identical frequency factors. So that's that A factor before the exponential. Reaction B has a higher activation energy than reaction A. Which reaction has a greater rate constant? So we could look at the Arrhenius equation and figure out, well, if this is bigger, what does this do to that? And that makes sense to some people, not to most people. Or we can think about this. So this is a conceptual question, so let's think about it. So we're looking for the greater rate constant. Is that the faster one or the slower one? Faster. So we're looking for the faster one. Oh, look, there I gave the answer away. Let's not do that. Too late. We're looking for the faster reaction. Okay, so I took that greater rate constant at room temperature and I kind of translated it into something that's a little more meaningful. I want the one that's faster. So reaction A and B have the same frequency factors, so that's the same. What's different is the activation energy. So if you just think about this in terms of playing miniature golf, the big hump or the little hump, which one are you going to get through faster? The little hump, right? Because you don't need as much energy to get over it. So the lower activation energy is going to have the higher rate constant. And so it's A. So this is a kind of question that people who hate math could do, because it's just thinking about ideas. But people who love math sometimes hate questions like this, because just ask me to calculate it. Just ask me to calculate it. Don't make me think about it, right? I'm going to make you think about it sometimes. And then that is where I stopped yesterday, so I'm going to stop there today.